Atlas LO2 at 10%.
Roger.
T-minus 1 hour, 17 minutes.
This is Atlas Launch Control, T-minus 1 hour, 16 minutes, 13 seconds, and counting. The launch window today is 2 hours in duration, extending from 1:28 to 3:28 p.m. Eastern Time. MAVEN has a 20-day nominal launch period with a daily launch window of 2 hours. Recent Mars missions have supplied conclusive evidence of flowing water on Mars millions of years ago. Surface features, imaged from orbit by cameras from such spacecraft as the Mars Reconnaissance Orbiter, show river networks, large basins, and glacier formations. Rovers such as Curiosity and Opportunity continue to collect geological evidence of ancient water, notably small-scale ripples preserved in rock formations and minerals that could have formed only in the presence of water. The Mars atmosphere is too thin and the temperatures too cold and dry. Surface water would either evaporate or freeze, since the temperatures average minus 64 degrees at the surface of Mars. Liquid water requires a thicker atmosphere and warmer climate. Discovering the fate of Mars water may depend on determining the fate of its atmosphere. And that is something that Principal Investigator Bruce Joukowsky will be discussing with us here in just a few minutes. All of our countdown operations continue on schedule. We're not working any issues either with the spacecraft or the Atlas V. And we're now at T-minus 1 hour, 14 minutes, 46 seconds and counting. This is Atlas Launch Control.
Atlas LO2 at 20%.
Roger.
Kilo 2 at flight level.
Roger.
LCRC-1.
Go ahead, RC.
That field mill that toggled off scale high is clear this time. Range is proceeding.
Roger.
T-minus 1 hour, 10 minutes.
Atlas LO2 at 30%.
Roger.
CISA ECS set point has been reset for 15 minutes minimum.
Roger. Initiate Centaur engine chill down.
Roger.
This is Atlas Launch Control, T-minus 1 hour, 9 minutes, 12 seconds and counting. Our countdown activities continue to run on schedule for 1:28 p.m. liftoff this afternoon. Joining us now is Vern Thorpe, the program manager from United Launch Alliance for our NASA missions. And Vern is going to talk to us some about the flight of the Atlas after it lifts off today, as well as discussing some of the things that are very special about this flight for United Launch Alliance and the community in Colorado and around Denver. So, first of all, let's go with the animation and tell us what we're seeing as the rocket lifts off.
Sure, George. This tape that you're about to see will give you a preview of what we expect to see later today. We're going to use an Atlas V vehicle to launch MAVEN. We're going to use our 401 configuration. It's a pretty big rocket, but it's actually our smallest Atlas V. You see liftoff there of the same configuration that we're using today. And since we have no solid strap-on rocket boosters, the first major event that you'll see after liftoff is when we've used up all the propellants in the booster tank and we shut down the booster engines and then separate that first stage from the rest of the vehicle. We will almost be in orbit at that time. There you see the engines shutting down. We'll activate a separation system and then fire some retro rockets to back that stage away from the rest of the vehicle. We then begin preparing for the first of 2 burns of the Centaur upper stage. And there you see our first engine burn. That first engine burn will last about 9.5 minutes. And 8 seconds into that burn, we'll jettison the payload fairing once we're above the atmosphere. Following that first 9.5 minute engine burn, we'll enter a coast phase. And if we launch at the beginning of the window, that coast phase will be 25 minutes long. After that, we'll be in position for our second burn, so we'll light the Centaur engine again, this time for about 5.5 minutes. And at the end of that burn, MAVEN will be on its way to Mars. And we'll do a few maneuvers to orient the spacecraft the way it needs to be. And then we'll separate it, begin a series of maneuvers with the Centaur upper stage to back it away from the spacecraft, and also adjust the trajectory enough so that there's no chance that it would ever impact Mars itself. So if we launch at the beginning of the window, it'll take a little less than an hour, about 52 minutes, to go from liftoff to spacecraft separation. If we have to move into the window for weather or for whatever other reason, the timeline could be extended up to 18 minutes.
Now, after the Centaur stops burning, I think you got indicated that there's actually a space in there of time between when the cutoff occurs and when the spacecraft separates. Is that right?
Yes, we're going to wait about 6 minutes to separate the spacecraft, and that's just 2 or 3 minutes longer than we usually wait, and that's just to make sure we've achieved all the pointing requirements and everything else that the spacecraft needs.
Well, Vern, this mission, this launch is a little unusual in what you could sort of call the Colorado connection. Could you tell us a little bit about why this is significant to Colorado?
Sure, I'd be happy to. Yeah, I mean, every time we launch one of these missions for NASA, it's kind of a showcase of what our country can do. But this mission really has a special meaning for Colorado. There's a lot of Colorado folks involved. I'm from Colorado myself. The science team that's behind this entire mission, led by Dr. Bruce Joukowsky, is from the University of Colorado up in Boulder. The spacecraft is built by Lockheed Martin in Colorado, and it will be operated by Lockheed Martin as well. And then, of course, United Launch Alliance, who I'm with, is headquartered in Colorado. So there's a very large number of Colorado organizations and Colorado people who are involved in this launch. And there's one other Colorado connection that I'd like to mention. We recently lost a great Coloradan who was also a pioneering member of the human spaceflight community. Scott Carpenter was born in Boulder, Colorado, and he passed away last month at the age of 88. And Scott was one of the original Mercury astronauts, and he actually flew to orbit on an Atlas rocket, predecessor of the vehicle you see here today. He was launched aboard an Atlas on May 24th in 1962 as cheering crowds lined the local beaches, and his flight was the second American manned orbital mission. He followed in the footsteps of John Glenn. Carpenter piloted his spacecraft through 3 orbits over a period of about 5 hours, and his goal was to demonstrate that humans could actually function and do work in a zero-G space environment. And when his mission was complete, he splashed down about 1,000 miles southeast of here, southeast of Cape Canaveral. His flight was obviously very successful for both himself, the Mercury program, for the Atlas vehicle, and it really helped lay a foundation for NASA space exploration. He and his fellow Mercury astronauts paved the way for NASA's march to the moon that led to the first lunar landing just 7 years after that. And over the years, Scott continued to be involved in the space community. He returned to KSC, the Kennedy Space Center, frequently to participate in various events, and he was here just last year for the 50th anniversary of Americans in Space. So in addition to launching MAVEN today, we're also taking time to remember and salute Mercury astronaut Scott Carpenter for his contribution to NASA's mission of space exploration.
Well, Vern, thanks very much. And it's kind of an interesting set of things that come together for this mission for Colorado, and the recognition of Scott Carpenter because he played such a significant role in the history of the manned space program for NASA.
Yeah, thank you, George.
Thank you very much. And we're at T-minus 1 hour, 3 minutes, and counting. This is Atlas Launch Control.
Atlas LO2 at 50%.
Roger.
T-minus 60 minutes.
LH2 chill down complete.
Roger.
HB's at flight mass.
Roger. Start LH2 tanking.
Roger.
Adjust TEM ECS temperature per TRD.
Roger.
LCRC1.
Go ahead.
At this time, range is proceeding with the exception of field mill rule 1 Bravo. Had another site kick over 1,000 volts, 2 nautical miles south of the pad. Estimated clear time 17:32 Zulu.
Roger.
Step 510, Atlas LO2 at 60%.
Roger. Initiate BRC ECS.
Roger.
T-minus 55 minutes.
Start flight control, final preps.
Roger.
This is Atlas Launch Control, T-minus 53 minutes, 56 seconds, and counting. We're joined now here in the Atlas Spaceflight Operations Center by Bruce Joukowsky. He is the MAVEN Principal Investigator for the Laboratory for Atmospheric and Space Physics at the University of Colorado at Boulder. Bruce, welcome, and I think I'd like to begin by asking you, it's been sort of interesting to listen to some of your conversation occasionally about the evolution of how this mission started almost 10 years ago on the back of a napkin.
It has been 10 years since we started this, and the original discussion was between me and two members of what became the science team of did we think that this science was competitive in the proposal environment, and did we think we could pitch it in a way that would win the competition, and where did we think we would stand in terms of how important this science would stack up against others. We did decide to go ahead with a proposal, and the colleagues I was talking with and I became the center part of the science team.
Well, then, as we went along, how does NASA go about a competition and awarding a particular proposal such as yours?
In this case, they had announced that there would be a competition to propose a mission, and all comers could put in proposals. We put together a team, put together a proposal that included the science, the instruments, the spacecraft provider, the management, the operations, everything involved. 20 proposals were submitted, and NASA selected 2 for further study, and after a year of further competition, they selected us to go forward with development for flight.
Well, let's go now to some of the science, because I know that one point that you've made fairly consistently is that in the big picture, the science involved with this mission has something to do with the habitability of Mars. Is that right?
That's right, and that's one of the questions we think is important for understanding Mars, looking at the history of the climate and the atmosphere. If we look at some of the data that has come back from previous missions, we see a lot of evidence for liquid water having flowed over the surface in ancient times. We see river channels, features that look like there had been lakes inside of impact craters. Other features, similar geological features. We see minerals that form only in the presence of liquid water. All of these suggest that there had been water on the planet early in time, and today, of course, we see a cold, dry, desert-like planet. If we want to understand what happened, what caused that change, we need to understand where the water went, where the carbon dioxide from a thick early atmosphere that supported the higher temperatures would have gone. And that's really what's driving us. By understanding the history of water, we understand both the history of the geology of the surface and the history of the habitability by microbes. Water is a requirement for life, and if we understand where the water has been and why it's not there anymore, we can learn more about what the history of the potential for life has been.
So how do we tie that into the atmosphere and the upper atmosphere?
Well, if you ask where did the water go, where did the CO2 go, it can go down into the subsurface. The CO2 can form carbon-bearing minerals, for example, but we don't see evidence for that. not in enough abundance to account for as much CO2 as would have to have been there. Instead, the other place it can go, the gases can go to the top of the atmosphere and be stripped away to space. The sun, the solar wind, they can drive processes that remove gas from the top of the atmosphere, and that's what we'll be studying. We want to understand whether the sun was able to remove gas from the top of the atmosphere and how much. If we can go to the first graphic here, this is a cartoon sketch showing the different processes that we think may have operated early in Mars history. I'm not going to walk through this. It would take a long time and bore everybody. But we designed the mission to understand each of these processes, starting with the sun input from the upper left, the solar wind, the extreme ultraviolet light, solar storm events, and then how they can drive different processes in the atmosphere. We selected the instruments to be able to look at each one of these processes and see how they operate today and understand how they could have operated in the past. What I'd like to do is go through just one of those processes and give you an example of how it works, and that's the stripping by the solar wind. As the solar wind goes by, it can grab ions and remove them from the atmosphere. We have a simulation coming up in just a second here that will show a computer simulation of how that stripping process works. Here we're seeing the planet. The colors represent the upper atmosphere. The arrows represent the solar wind going by. And you can see that the gas is just being picked up and streamed away. This is a very tenuous part of the upper atmosphere, so we're not talking about a lot of gas, and it's a very slow leakage rate, if you will. But early in history, when the solar wind was more intense, when the solar ultraviolet was more intense, we think that the escape rates would have been greater. So by looking now and seeing processes like this, we think we can understand what happened 4 billion years ago.
Well, Bruce, where will your team actually be when they first see some of this science coming in?
We have a distributed science team, and some of the members will be at the University of Colorado, where I'm stationed, at University of California, Berkeley, at Goddard Space Flight Center, and at several other institutions around the country and a couple abroad as well.
And you expect to start seeing some of that science when for the first time?
We go into orbit in late September of next year. It takes us about 5 weeks to commission the spacecraft to get ready to do the observations, and then we'll start to get the measurements. I'm thinking that it will take us about 3 months to be sure we understand how the instruments are working, make sure they're calibrated properly, and we can begin to understand what the data are telling us. So I think we're looking at beginning to have some of our key science results starting early in 2015, about 14 months from now.
Yeah. Well, Bruce, thank you very much, and sure your team has with so much effort over the years to put this mission together. This is coming to a pinnacle, an apex here in just less than an hour.
This is incredibly exciting, and you're sitting here with the same view that I've got of the rocket on the pad up on the screen here, and we're just excited right now and hoping for the best.
Bruce, thanks very much.
Thank you.
And we're at T-minus 46 minutes, 7 seconds and counting. This is Atlas Launch Control.
LH2 70%.
Roger.
LH2 at 80%.
Roger.
T-minus 43 minutes.
Atlas LO2 at 90%.
Roger.
LH2 at 90%.
Roger.
T-minus 42 minutes.
ECB at flight pressure.
Roger.
RCN1.
Go ahead.
Roger that. I was reporting that we are now green on all weather constraints. Range is green.
Roger.
T-minus 40 minutes.
Start final open loop FTS test.
Roger.
Step 570, Atlas LO2 at 97.5%, topping started.
Roger. All steps are complete through step number 590.
Step 620, Centaur LH2 at 96.2%, topping started.
Roger. Perform Centaur LH2 fill and drain valve cycle test.
Roger.
Perform Centaur LO2 fill and drain valve cycle test.
Roger.
Centaur LO2 fill and drain valve cycle test is complete.
Roger.
Step 630, Centaur LH2 fill and drain valve cycle test complete.
Roger. Perform Centaur SRV and LH2 SVV cycling test.
Roger.
This is Atlas Launch Control, T-minus 35 minutes, 25 seconds, and counting. As we've heard, we've completed the cycling of our fill and drain valves on the Atlas and Centaur, and we are continuing without any issues on the vehicle whatsoever. We have some additional tests coming up we've got a fill and drain valve test on the Atlas test right now, and a functional test. See the Coast Guard offshore there patrolling the waterways and security, NASA security. Right now, the only thing going on is our launch weather officer, Clay Flynn, reports that some of the field mills, which measure the electrical potential in the area, are beginning to toggle back and forth between the acceptable limits and are being watched with some indication that there is a cirrus anvil cloud overhead that makes those field mills at time go out of specification. But right now all the field mills are green. But that's something that may happen as we have some clouds begin to move into the area of the field mills that measure electrical potential could go in and out of limits. So at the moment we had one go out, now it's back in, and at the moment we're green. But that could continue to happen about any time through the balance of the count and into the launch window, as long as we have some cloudiness approaching us from the northwest. Otherwise, we're continuing with our fill and drain valve cycling. We've completed the first round of that and going into concluding that activity, which will keep us completely on schedule for a 1:28 p.m. liftoff. At T-minus 33 minutes, 16 seconds and counting, this is Atlas Launch Control.
Are complete.
Roger. Resume Centaur LH2 topping to flight level.
Roger.
Resume Centaur LO2 topping to flight level.
Roger.
LC Redline Monitor.
Go ahead, Redline Monitor.
Yes, LC at T-minus 43:15 approximately. Redline Monitor indicated an OTC on measurement Charlie Uniform Kilo 020 Echo. That is a Centaur liquid oxygen delta pressure measurement.
Roger. Centaur Pneumatics, LC.
Centaur Pneumatics.
Roger. You observing any problems with tank pressures? Or did we maybe pick something up during the vent valve test?
I don't see anything out of the ordinary. The Centaur vent valve cycle test seemed to be nominal. What was the measurement again?
Charlie Uniform Kilo 020 Echo. Okay. Tank pressures at this time are indicating nominally.
Tank pressures at this time are indicating nominally, correct.
Roger. AC, LC, channel 1.
ACN1.
Roger. Redline Monitor reported a OTC violation on Charlie Uniform Kilo 020 Echo, Centaur LH2 Delta P measurement. Please convene the anomaly team and provide a recommendation.
Roger.
T-minus 31 minutes.
LC is Redline Monitor.
Go ahead.
Yeah, we've been reading in band on that measurement Charlie Uniform Kilo 020 Echo for some time now. Could we go ahead and reset that violation, acknowledge that?
Roger, reset it at this time.
Roger, in work.
This is Atlas Launch Control, T-minus 25 minutes 45 seconds and counting. Today's launch is dedicated in memory of Grover Hall and Adam Crocker. In his 39-year career, Adam Hall with Lockheed Martin Space Systems and also Adam Crocker held a number of key engineering management positions, including a vice president of NASA Systems, overseeing Magellan, tethered satellite, and flight telebotics resurfacer. Adam Crocker was a student at Colorado State University, an Air Force ROTC cadet, a pilot, and a young man interested in space. His father, sister, and brother-in-law are members of the spaceflight community at Lockheed Martin and United Launch Alliance, who have all been involved with the MAVEN mission and the Atlas program. So again, our dedication of this launch to Grover Hall and Adam Crocker.
LC, step 810, FTS open loop test is complete.
Roger.
LC, ALO.
Go ahead.
Step 640, Atlas LO2, fill and drain valve cycle test complete.
Roger.
Atlas airborne vent valve functional test is complete.
Roger. Perform pogo suppressor charge.
Roger.
This is Atlas Launch Control, T-minus 21 minutes, 33 seconds, and counting. The Atlas V rocket has two stages. The Atlas booster stage is 106.5 feet long, 12.5 feet in diameter, and it burns two propellants. RP1, which is a highly refined kerosene. There's approximately 26,000 gallons on board. And liquid oxygen. There is approximately 50,000 gallons loaded on board the Atlas. The Centaur stage is 41.5 feet long, 10 feet in diameter, and it burns liquid hydrogen and liquid oxygen through its RL-10 engines. There's approximately 12,000 gallons of hydrogen loaded aboard now, the Centaur stage, and 4,000 gallons of liquid oxygen. The height of the vehicle on the pad is 191 feet. And it will weigh approximately 750,000 pounds at liftoff. Right now we're not working any issues. The field mills currently are green, and they may drift in and out occasionally with the encroachment of some cloudiness from the northwest. And the one other indication that we were working was associated with our fill and drain valves is apparently a transducer issue and does not appear to be a concern. So we're at T-minus 19 minutes, 33 seconds and counting. This is Atlas Launch Control.
LC, ALO.
Go ahead.
Step 690, pogo suppressor charge complete.
Roger.
T-minus 19 minutes.
LC Flight Control Channel 1.
Go ahead, Flight Control.
Step 750 BRC SIB1 and SIB2 voltage checks are complete.
Roger, LD. NLM, Channel 1.
NLM's on.
Roger.
LC, AC on 1.
Go ahead.
Roger, sir. I'm ready to provide the outbrief for the red line monitor issue.
Proceed.
Roger, sir. The team has reviewed the data associated with measurement Charlie Uniform Kilo